All right. Good. Hello. I know that last video was long, so let me know if you have any questions and how I can help you. But this video is shorter, but it does deal with something very important. We'll spend a good amount of time on it. There are some professors in the Penfield College informatics program that feel that proofs, which we're beginning to talk about here, are a very important part of this class. So we're going to try to help you develop the ability to prove things and know the surety of statements and a sequence of statements, whether they're valid or not. Now, Rosen says that proofs in mathematics are valid arguments that establish the truth of mathematical statements. Okay? By an argument, we mean a sequence of statements that end up with a conclusion. By valid, we mean that the conclusion or the final statement of the argument must follow logically from the truth of the preceding statements or premises. So the premises are the beginning statements that you're given to be true, and from those premises you draw other statements that you can logically deduce from these until you reach your conclusion. Now that's one form of proof where you go directly from the premises all the way down to the conclusion. But there are other types of proofs that aren't so direct, and we'll talk about those. But this is section 1.6 in Rosen's text, Rules of Inference. Okay. Now, here is an example of an everyday argument that you might hear. Example, if you discover the password, then you can change the balance in the account. You have discovered the password, therefore you can change the balance in the account. Okay, now this is the most direct argument you could have. It's the most simple, pretty much. So here's how we would write this symbolically. Now the first statement, if you discover the password, then you can change the balance. So if I'm going to represent, let D be you discover the password, and then let C be you can change the balance. Then you could write this as if D, then C, or in other words, D implies C. All right. Then the next premise is that D is true. So if we just write D, we're stating D is true. Okay. Now I wrote the words is true in parentheses, but you didn't have to. You could have just written D. All right. So the conclusion is therefore C is true. Now why does that hold true? Well, an if-then statement, if that is true, and if the first part is true, then the second part is going to be true. Okay. So the form of this argument is premise 1, premise 2, and then the conclusion. But in symbols, the logical symbolism is D implies C, D is true, therefore C is true. And you see those little 3 dots means therefore. All right. Let's look at another case, or let's look at a set of possible valid arguments. So this is a table that gives several, it's not exhaustive, but it gives several valid arguments that you could use to form a proof or to form just an argument in everyday speech. So let's look at this table. In the first row of the table is the argument that we just gave. The order of the statements is a little bit different, but here it is. P is true. If P, then Q, therefore Q is true. So that direct going from the if part to the then part the if part is true, therefore the then part is true. That is called modus ponens. Modus ponens, okay? Now, if you do a truth table and you do this statement that P is true and if P then Q, that implies Q is true. If you do a truth table for this, you will find that it is a tautology. Okay, in the second row of the table, this says that if you know Q is false, so not Q, and you have the implication if P then Q, then you know that P is not true. Okay? Now, forming this, if you take the not parts of this, it's basically saying if Q is not true, then P is not true. Now think about that. If Q is not true, then P is not true. What is the relationship of that to the implication if P then Q? Well, if you think about it, if we have if P then Q and we switch them around and negate them, not Q then not P, we have really formed the contrapositive. And so the reason that this second row, which we call modus tollens, is true is because the contrapositive is logically equivalent with the original statement. So if you have, the situation not Q is true, then and also if P then Q, therefore you can conclude that P is not true. Okay. So for example, if I have the statement, if talking about my granddaughter again, if my granddaughter picks up her toys, then we'll go to the park. So that's the P then Q. All right. Well, if it was not true that I took her to the park, then it must be not true that she cleaned her room. Okay? Because if she had cleaned her room, I would have taken her to the park, if my original statement is true. So you can see that if I did not take her to the park, then she must not have picked up her toys. So that's called the contrapositive, but as a rule of inference, it's called modus tollens. Okay. The third row sort of forms a chain of if-then statement. It says if P then Q, if Q then R, therefore if P then R. All right. So it's kind of like in math, if A is equal to B and B is equal to C, then A is equal to C. It's a little bit different than that, but it's similar, all right? The difference is in math, if A is equal to B, you can switch it around and say B is equal to A. But in logic, you can't necessarily say that if P then Q means if Q then P. You can't switch around the statements. But as long as it's going that one direction, if P then Q, if Q then R, therefore if P then R. That's called a hypothetical syllogism. Hypothetical syllogism. Now, the next row uses or, and it says if P is true or Q is true, but P is not true, then it has to be that Q is true. Okay? So for example, if I said you will either, do your homework or you will fail. If that's true, if you did not do your homework, then it must be that you failed. Or if you did not fail, then you must have done your homework. It's got to be, one or the other. That's called a disjunctive syllogism. Okay. Now the next couple are kind of pretty obvious. The addition rule says that if P is true, then you can make the statement either P or Q is true. Okay? Now, with the next one called simplification, it says if you know P and Q, that whole statement is true, well, then you know both of them are true. Therefore, you can state that one of them is true. Of course, they both have to be true, so one of them is true. And you could also state Q is true as well. All right, and then conjunction is a way, if you know both of the statements are true, then you can say that the conjunction of them is true. All right, and then the last one is called resolution, and you can see the form of that. Explaining it is a little bit difficult, but P or Q, not P or R, therefore Q or R. And this is based on the fact that either P has to be true or not true. So anyway, all right. Now look at this example here. It says, if it snows, the roads will be slick. If the roads are slick, there will be many accidents. Therefore, if it snows, then there will be many accidents. Okay? So I've symbolized if it snows as the letter S. I've symbolized roads as roads will be slick as R. Of course, I don't want to use S and S, you know, snow and slick. I say snowing is S, roads being slick is R. And then I also called there will be many accidents. I called that A. So the second statement, if the roads are slick, so if R, then A, there will be many accidents. So the conclusion is, if it snows, then there will be many accidents. Now notice the conclusion, it doesn't say whether it's going to be snowing or whether there's an accident. It just says if it does snow, then there will be accidents. So it's called a hypothetical syllogism. All right, and that's the third row of the table. All right, so we'll be looking at other examples of these items in the table. Now, another argument example, in English words, the operating system is new or it can support encryption. So you got an or situation. But we have found that the operating system is not new. So that's basically saying it's not new. Therefore, it must support encryption. Okay? Now in symbols, if we let N be the operating system is new, we let E be it can support encryption, then we can write the first statement as N or E. Now the second statement says the operating system is not new, so that's not N. And then the conclusion is, therefore, it must support encryption. So what you have to do is write this in symbols and then look at the rule of inference table and determine which of those rules of inference are being used. Now, if you're not using one of those rules of inferences, then it probably is not a valid argument, okay? Because those rules of inferences are what you're responsible for knowing, and I'm not going to throw something that's not on the table, but it's still valid. So it'll be something in the table if you correctly get it written in symbols, all right? Well, as you may have noticed, this is what we call, where'd it go? It's the fourth row down, disjunctive syllogism. So P or Q, not P, therefore Q. All right, so that's a disjunct. So the answer to that example is, when I ask which rule of inference is disjunctive syllogism. Okay. All right. So next, this is taking several statements and putting them together into a chain of statements. Okay. So here's an example. If you get the loan, we'll call that L, then you will be able to start your business. So we'll call that B. So that first statement could be written as L implies B. If you don't get the loan, you will go back to your old job. So that'll be J. Now, if you don't get the loan, that would be not L. So if not L, then J. So that's written in the premises as the second premise there. Not L implies J. The third sentence, if you go back to your old job, then you will never be able to buy a house. That would be not H. Okay, so we would say if J, then not H. Okay, so what we have to do, final statement. Okay, what we have to prove, I'm sorry. Prove that this means that if you do not start your business, you will never be able to buy your house, to buy a house. So if you do not start your business, so that's not B, then not H. Okay, so that's what we have to prove. All right, we have to see if the premises lead to the conclusion. Okay, so let's look at this. All right, so we start off, now you don't have to start off with the first premise. You could start off with the second premise or the third premise, but you generally start off with one of the premises. And so we write if L, then B. Now, why do you think that we did the contrapositive of the first premise? Well, because that not L right there in the second premise, the not L is helpful. Okay, not L is helpful because the second premise begins with not L. So if we take our first premise and do the contrapositive, in other words, we're going to switch around the L and the B and negate both. So not B, then not L. That lets us chain or connect that with the second premise. Okay, so the second premise begins with not L, implies J. Okay, now what we're going to do is take statements 2 and 3 and use hypothetical syllogism on 2 and 3. And basically it gives us a single statement. If not B, then J. Okay, so we combine those two and get sort of a combined statement. If I don't start the business, then I'll have to go back to my old job. And then we just state the third premise, which is if you go back, if you're in your old job, then you will not be able to buy a house. If you put that statements 4 and 5 together using hypothetical syllogism again, you can get that if not B, then not H. So if you do not start your business, then you will not get the house. So I hope that you can sort of sense how these statements can be put together and why we had to do the contrapositive of one of them. You can use any logic rule of inference to create another statement. You can use addition or simplification to create another statement or conjunction. All right, so let's look at what we call fallacies. Okay, now fallacies are times when people wrongly make logical conclusions. Okay, so here's an example. If no one calls him, then he will go fishing. He went fishing, so it must be that no one called him. Okay, why is this wrong? Well, it takes the statement, if no one calls him, then he will go fishing, and it sort of switches it around. It says he went fishing, therefore no one called him. That's implying the converse. the converse of P then Q is Q then P, but it's not logically equivalent with the original statement. If I say, if it's raining, then there's clouds in the sky, that is not the same as if there's clouds in the sky, then it's raining. You have to be able to realize that you can't switch a if-then statement around like that, okay? That's called the fallacy of affirming the conclusion, okay? So, you know, he went fishing, so that's the conclusion of the statement. You have a hypothesis and you got the conclusion. You state that the conclusion is true, so that means the hypothesis is true? No, not necessarily, okay? So that's a false argument or invalid argument, all right? The second example, if you submit the application, then you will be interviewed. You did not submit the application, so you will not be interviewed. Now, does this say that, you know, there aren't any other extenuating circumstances why someone would get interviewed? Does the original statement say that? No. It just says all those who submit an application will be interviewed. It doesn't say that if you don't submit an application, you will not be interviewed. That's called the inverse of the statement. So in symbols, if S, then I, so if you submit an application, then you will be interviewed. Not S, therefore not I. So you're falsely implying the conclusion because you can't just negate the if and the then parts, and you know the inverse, which is right here. Why is my cursor not okay? Not S implies not I. That's the inverse of S implies I. All that was done was you negated each thing. You didn't switch them around. Now, if you had switched them around and negated them, that would be called the contrapositive, and that would have been logically equivalent. So it would have been a valid argument. But in this case, you can't say that the inverse is equivalent with the original statement. So this is an invalid argument, all right? Law of modus ponens, called the law of detachment also, uses the original statement, if P, then Q. So if you know P is true, then Q is true. And so that's a valid argument. The law of modus tollens uses the contrapositive, which is right here. Not Q implies not P. Okay? Not Q implies not P. And because we both switched and negated the statements, we're using the contrapositive. And so if you have not Q, then you can conclude not P. That's a valid argument. Modus tollens. But the argument above, as I was saying, uses the inverse, and that's not valid. This is called the fallacy of denying the hypothesis. There's affirming the conclusion, fallacy of affirming the conclusion. There's also the fallacy of denying the hypothesis. And you can't make a statement from that, a valid argument from that, okay? Now, if you go to this website, fallacyfiles.org/taxonomy.html, it has a whole bunch of fallacies that you can look at. You don't have to know all those, but you should recognize the phrase fallacy, what that means. It's basically an invalid argument. Okay, let's move on. So rules of inference for quantified statements. So now we're going to look at the quantifiers. All right. So if you look at this table here, as you know, the upside down A means for all A, and P of X is some fact or proposition about X or function of X, okay? So the first rule of inference is called the universal instantiation. So what it says is, if you know the premise for all X, P of X is true. If you know that premise, then you can say that P of C is true for some particular X. In this case, C is the value we're using for X. So C is like a particular value. You've got a generic X in the original premise. For all X, P of X is true. But now we're saying there's a particular, if C is one of those X's in the domain, then P of C is true. Okay? Now, the next statement is a generalization that basically says if you know that for any C you pick, any particular C you pick in the domain, P of C is true, then you can say for all X's in the domain, P of X is true. So it goes from, if you know some arbitrary C, not just a single one, but any one you pick, then P of C is true. Therefore, for all X's, P of X is true. Okay? So in proofs, sometimes we'll say, let's pick a particular value of X and call it C. Okay? So it's just an arbitrary one you called C, so it's representative of any one of them. And then we prove that it works for that one, then we can make the generalization that it works for all of them. Okay? So that's really what this second statement here says. The symbol there exists means, that's what the second rule states, that if for any arbitrary C, P of C holds, then for all the X's, P of X holds true. Okay, looking at the third line now, existential instantiation. This says, if you know that there exists an X in the domain where P of X is true, then you know P of C is true for some particular C value, for some element P of C. So we can sort of now launch out and use that fact on some. We don't know which one, but if you know that there exists some out there, we can call it C and then use the fact that P of C is true. And then the fourth rule kind of goes the other direction, says if P of C is true for some element C, so this is a particular one that we found that P of C works for, then we know that there exists an X, a generic X. There exists one of those in the domain where P of X is true. Okay? All right, so now let's look at combining some of these rules of inference for propositions and quantified statements. All right, this is the last slide. So universal modus ponens is where we have a universal statement that for all X, if P of X is true, then Q of X is true. Okay, so it's a universal implication that for all X's, if P of X is true, then Q of X is true. Okay, well, then we can, if we know that P of A is true for a particular A value in the domain, then we can conclude Q of A is true for that particular element. All right? So if we know that the if-then statement holds for all X's, then we know that if the first part, the P part, is true for a particular element, then Q is true. And then universal modus tollens says for all x, P of x implies Q of x, if you know that is true, but then it's not true that Q is true for a particular A value. So in other words, not Q of A, then we can say not P of A. Now this uses the contrapositive because it negates the conclusion. So it's not Q implies not P. So it's not only going in the opposite order, but we negated both of them. That's the contrapositive. And so it's universal modus tollens. So here's an example. Now I've changed this from what was in the notes, but it should be correct now in the notes. If you just downloaded it this week, should be fine. But anyway, suppose we know that if x is greater than 4, then the square root of x will be less than x divided by 2. Okay. So I'll give you an example. So we'll pick an x that's bigger than 4. Let's say 10. Okay. So this statement basically says, since 10 is greater than 4, then the square root of 10, which is really about 2 point something, I'm sorry, 3 point something, is less than 10 divided by 2. Now 10 divided by 2 is 5, and obviously 3 point something is less than 5. So this quantity, this inequality here, square root of x is less than x over 2, holds true whenever x is greater than 4. All right. Now we can use modus tollens to argue that if the square root of a is greater than or equal to a over 2 for some particular a value, then that a is less than 4. Okay, that particular a value is less than or equal to 4. So why can we use that? Well, do you notice that the inequality has been switched around? So this is like the opposite. So we're saying that if the opposite, so this is the not Q of A, so this harks back up to this universal modus tollens. So if not Q of A, so square root of a is not less than, so it's greater than or equal to a over 2, then a would be, well, then not greater than 4. Well, what's the opposite of not greater than 4? It's less than or equal to 4. So we just basically are using this fact to get that a must be less than or equal to 4. All right. Okay, the next example, if you know that when n is greater than 1, 1 plus 2 plus 3 all the way up to n is equal to this formula when you plug in n. So in other words, you know it's true that whenever n is greater than 1, this property will hold true. Show that 1 plus 2 plus 3 all the way to 9 will equal 45. Okay? Well, what is n in this case? Well, it's a particular value. N is 9 here. You see that, if you look at the form, we ended at 9. So in this case, we ended at 9. So n must be 9. And is 9 greater than 1? Yes, of course. So the P of x is true. So looking at the universal modus ponens, P of A, in this case 9, P of 9 is true because 9 is greater than 1. Well, it holds that it follows by universal modus ponens that I can plug 9 into the Q part. The Q part is the right side of this, that 1 plus 2 plus 3 all the way to 9 would equal this formula. So what happens when I plug in 9 here? 9 times 9 plus 1, well, that's 10. So 9 times 10 is 90. 90 divided by 2 is 45. So you just show that, a little bit of scratch work to show that. And you have actually used universal modus ponens to basically apply this formula to a particular value of n. Okay, so I know it seems complicated, but it's just we're giving a name for things we're already doing in some cases. But I hope that you can work on the problems and do okay with them. But please let me know if you have any issues. Okay. All right. That ends the lesson for all of week 1. And so you want to work on the homework first and then try the practice problems to prepare for the quiz. All right. Have a good night.